Okay, good afternoon, everybody. My name is Guy Davidson, and I'm the Principal Coding Manager at Creative Assembly. I've been there for quite a long time, since 1999, in fact. I love working there. It's great. One of the things I get to do is write lots and lots of code. Today, I'm going to be talking about specializing linear algebra for geometry. Particularly, I'm going to be talking about geometry and what we might want from geometry in the standard. But before I start, I want to talk about this group, hash include. There's a big problem in the C++ community. There are disproportionately few women and ethnic minorities represented here. And if we were in a room, I would imagine that this room would be similarly underrepresented. This is a big problem for hiring and solving the big engineering problems that we face. There just aren't enough of us. You can help by joining in the effort of the hash include Discord server and help us to reach out to these groups. And if you want to be a useful member of the C++ community, you can help by recruiting from outside of the community demographic. Thank you. Now, this is what to expect. You'll see a brief history of geometry. And then we've got linear algebra and geometry, lines and curves, polygons, regular and irregular, intersection and precision, and then a summary of classes and expected functions. The numbers in square brackets are the slide numbers. You'll see there are 154 slides. There aren't really 154 slides. I'm just not very good with doing slide animations, so I have a fresh slide for each animation. Don't worry, it's not as huge as you might expect. So if you come up with any questions, note down what the slide number is. It's in the bottom right-hand corner there, and we'll address those as time goes on. Now, let's talk about geometry. So geometry is an ancient endeavor. It is the branch of mathematics concerned with questions of shape, size, relative position of figures, and the properties of space. And it was also a favorite topic of mine at university. I am a mathematician by training. Time is short. So I want to draw attention to two people whom you will have heard of, particularly if you're attending Walter's keynote this morning. So the first of those, of course, is Euclid. And the second is this fellow here. His name is Descartes. Now, Walter did mention Euclid's Elements, and I wonder who here has read it, all 13 books. It is actually quite an easy read. Well, for the sort of person who's going to attend this talk, it's an easy read, and there's lots and lots of pictures. Up until the beginning of the last century, up until about 1900, it was presumed, and certainly in England it was presumed, that anyone who was educated would have read it. Not necessarily in the original ancient Greek, although you'd have got bonus points for that. I found a PDF. Bound copies to improve your bookshelf are easily available from Amazon, so I do recommend taking a look at it. So we'll start with the first of 48 propositions, and this arrives after 23 definitions, 5 postulates, 5 common notions, and a diversion on the third person present perfect imperative in my translation, which is contained in book 1. There we are. Clear as the river Neva. Here's the English version. How to construct an equilateral triangle given a finite straight line. Create 2 circles of the radius of the straight line, put their centers at either end of the straight line, and where those circles intersect is the third point of the equilateral triangle, since all points of the circumference are equidistant from the circle's center. This is magnificent. Book Elements set the tone for mathematics, and it's looked pretty much like this ever since: definitions, postulates, and propositions. Now, geometry got us a long way in road and canal building, navigation, architecture, astronomy, all sorts of human endeavor, but it wasn't until the 17th century, nearly 2,000 years later, that the next great leap forward happened. And this was the work of René Descartes, one of the founders of modern philosophy. He's probably best known for mind-body dualism and a particular Monty Python song. But we're more interested in his contribution to mathematics. Now, according to Descartes' biographer, the story goes that during the night of November 10th, 11th, in 1619, while stationed in Neuburg an der Donau, Descartes had 3 dreams, and he believed a divine spirit had revealed to him a new philosophy. Particularly, he formulated analytical geometry, and it's hard to overstate the impact Descartes had on mathematics. But this isn't a history of mathematics lecture. I'll let you research that yourself, but do take a look at his extraordinary contribution. Now, analytical geometry works by introducing a coordinate system and giving every point in the plane a pair of real number coordinates. Now, if this was a film with a soundtrack, with a big orchestra, you would probably hear some cellos and some trombones playing serious music, as this foreshadows a significant problem with geometry in programming. We'll return to it later. Real number coordinates. Now, the most common coordinate system is the Cartesian system. So this takes the real number line and rotates a copy through 90 degrees. So each point is represented as an ordered pair of distances along each axis, horizontal then vertical. Now, less common is the polar system, where each point is represented as a distance from an origin and an angle of rotation. This is incredibly useful when working with rotations, but not so much when looking at straight lines and linear motion. And also, orientation is problematic. Do we measure clockwise or anti-clockwise? Mathematicians go anti-clockwise from y equals 0 because the number line goes left to right. Engineers, on the other hand, they go clockwise from x equals 0. And if clocks have been invented in the southern hemisphere, it would be a different matter, as clockwise and anti-clockwise would be reversed. Sundials, you see. Of course, this can be extended into 3 dimensions by adding an additional axis, or indeed any number of dimensions, but I'm not going to cover that here. The treatment of a torus as a 4-dimensional object blew my head off while I was at university. But now that we have algebra to work with, we can start work using equations and models rather than pictures. So let's start with a straight line. Rather than, as Euclid did, just drawing a straight line on the page and simply connecting it to other lines and curves, we can define a frame of reference and describe a line as a set of points satisfying particular properties. And here we have a line. It's the set of points x, y in R such that y minus 2x minus 3 equals 0. How do we algorithmically compute the full set of points? Well, thanks to algebra, we can arrange this equation to y equals 2x plus 3. And all we need to do is go through every value of x and retrieve the corresponding value of y. Now, you will recall from your elementary education that these 2 constants have names, the gradient and the y-intercept. And this gradient is what allowed Newton and Leibniz to come up with differential calculus. Of course, straight lines are not the only object of interest. Modeling curves is a big topic. Let's look at a simple parabolic trajectory. This curve is a quadratic curve, typically made by throwing a ball in a vacuum. And I'm sure we've all thrown balls in vacuums. It's the set of points x, y in R such that y plus x squared equals 0, or y equals negative x squared. Now, one problem we have with this is that all our curves have a unique value, a unique y value for each x, and so can be expressed as a simple equation. Unfortunately, closed shapes like circles, well, that's simply not the case. So this is the set of points x, y in R such that x squared plus y squared minus 3 equals 0. Now, this doesn't rearrange to a simple equation, but what we can do is establish the points parametrically. We can introduce a third value, t, and range it from 0 to 2 pi, so that we can describe the circle as the set of points xy in R, such that for t in R and t between 0 and 2 pi, x equals 3 sine t and y equals 3 cos t. Now, finding models for shapes is fun, but what about arbitrary curves? Things get more interesting now as we have to worry about continuity and angles and asymptotes and all manner of nonsense, but we will return to this topic in a little more detail later on. And I, of course, need to remark on other fields of geometry. My intention in this talk and with my upcoming paper is to particularly address the problems of modeling the physical world. It will be enough to introduce a coordinate system for 2 and 3 dimensions. However, analytical geometry is not the only game in town. If any of you have been to CERN, or if you've done a shift there, you'll know all about differential geometry, which uses techniques from calculus as well as linear algebra to study problems in geometry set in differentiable manifolds. And it's where topology and differential equations intersect. Non-Euclidean geometry first got its start in this field, characterized by things such as diverging parallel lines. Algebraic geometry is becoming the linear algebra of the 21st century, feeding into many of the emerging fields of mathematics. Wiles used it to solve Fermat's last theorem. And geometric algebra is also a thing. It's the preferred mathematical framework for physics. And I could go on, but the point is that we need to qualify geometry with Cartesian or analytic to be absolutely sure of what we're talking about, which has ramifications for any paper. What do we name our include header, or rather our module? It's tempting to type hash include geometry or import geometry, but that might generate complaints. How about hash include Euclid or hash include analytical geometry? The joys of bike shedding are enormous, and I look forward to this point. Now, yet more fundamental than analytic geometry is linear algebra, and last year I started work on a linear algebra library for the C++ standard with Bob Stiegel, and I've spoken at several conferences on this matter, so I'll present a brief summary of how this library is going to work for the sake of further content in this presentation. But first, I'm going to just check and see if there are any questions. There seem to be none at all. Fabulous. Okay, let's move on. Now, let's look again at the general form of a linear equation. Now, we can migrate this to the 2D plane with a little substitution. And then more familiarly, we can turn this into ax plus by equals c, and that becomes by equals negative a times x plus c. And since b and negative a are arbitrary constants, we can see that y equals mx plus c, which is the very familiar equation for a straight line. So we can see that any straight line can be represented with a linear equation. Generalizing to 3 dimensions, you can see how this would work for planes. Now, representing a coordinate pair as a vector like this, x, y, we can translate, scale, shear, reflect, and rotate this vector. So translation takes place by adding the translation to the coordinate pair like this. Scaling works like this, either by a scalar multiplication, or we can achieve the same effect with a matrix multiplication. Shearing means scaling x and y by different amounts, which we achieve in this way. Reflecting means multiplying a particular ordinate by -1. And finally, rotating, slightly more complex, requiring this matrix multiplication. The linear algebra proposal offers a vector and a matrix class template. The API is dull and uninteresting, and it's exactly what you would expect it to be and should not require teaching if you know what a vector and a matrix is. And this is the point of an API. The template parameters are far more interesting. We can specialize for fixed size vectors and matrices of size 2 or 3 or 4 floats. But of course, I'm not the first person to decide that what C++ needs is a geometry library. We must consider the prior art. So let's look briefly at Boost Geometry. Now, this venerable library has been part of Boost for about 10 years now, and it's authored by Barend Gerels, who works at TomTom. Now, from the introduction, Boost.geometry, aka Generic Geometry Library, GGL, part of the collection of the Boost C++ libraries, defines concepts, primitives, and algorithms for solving geometry problems. So Boost Geometry contains a dimension-agnostic, coordinate system-agnostic, and scalable kernel based on concepts, metafunctions, and tag dispatching. And on top of that kernel, algorithms are built: area, length, perimeter, centroid, convex hull, intersection, within, distance, envelope, simplified transform, and much more. The library supports high-precision arithmetic numbers such as TT math. Now, it says based on concepts. This is an old description that predates concepts as we know them, just to clear up any confusion there. Now, Boost Geometry contains instantiable geometry classes, but library users can also use their own. Using registration macros or traits classes, their geometries can be adapted to fulfill Boost Geometry concepts. So Boost Geometry might be used in all domains where geometry plays a role: mapping, geographic information systems, game development, computer graphics, widgets in GUIs, robotics, astronomy, all sorts. The core is designed to be as generic as possible and support those domains. But for now, the development has been mostly geographic information systems oriented. So this gives us a great starting point. Let's look at what's on offer. So first of all, Boost Geometry is dimension agnostic, using the same interface to support 2D and 3D operations. Note that the linear algebra proposal is also dimension agnostic. It's also coordinate type agnostic. So we can use integers, floats, or anything you choose, just like the linear algebra proposal. Feeling pretty good so far. So we have dimension and type agnosticism. So let's consider a distance function. Now, we want the shortest distance between any two things. For example, 2 points, a point and a line and a polygon, a point and a polyhedron. And these will all have different algorithms. Calculating the distance between 2 points simply requires the application of Pythagoras in the appropriate number of dimensions. The point-line case requires extending the line, projecting a normal to the point and seeing where the intersection is, choosing the closest endpoint if there is no intersection. But this is not really any different from the linear algebra case of addition, where different shapes of matrices demand different addition algorithms. Again, we have a parallel with linear algebra that we should be able to exploit. Boost Geometry also offers functionality independent of coordinate systems. Indeed, everything looks pretty rosy, but there is one thing that Boost Geometry doesn't offer, which is the way of describing curves. Right, a couple of questions have just emerged. The first one is, do we expect the vector and matrix types in the library to be usable outside of geometry problems? We absolutely do. The point of this talk is about specializing linear algebra for geometry. Linear Algebra Library is a general purpose linear algebra library for as many rows and columns as you want, and indeed for quantities of row and column that you don't know at compile time, where you don't necessarily own the storage, where you're viewing the data with and applying a strides to it. This is simply one particular use of it. The reason why I wanted to create a linear algebra library was to support geometry. But with such a thin use case, there's not going to be much demand. There are many just absolutely huge uses of linear algebra, particularly machine learning, where we're looking at matrices with billions of elements inside them. So we need to be able to support many, many use cases besides simply geometry. But for the purposes of this talk, I'm just going to talk about geometry. And the second question, tying into Joshua's question, does it involve such things as expression templates? It's up to you. It can do. The approach that we're taking with linear algebra is to not provide an implementation, but to simply specify how it should behave and to not constrain the return types of all of the linear algebra functions with a type. So all of the functions, which are all function templates, simply return auto, which allows you to return expression templates, to use expression templates to return different types of objects that are composites in how you might wish to make up your final computation. This allows you to achieve all sorts of really neat optimizations like loop fusion. There's nothing to stop you ultimately from providing your own implementation and your own specialization at the precise granularity that you want. I don't know if by default the implementers will provide expression template versions of the library or will simply provide naive const expra kernels for all of the operations, but that will be down to the implementers. Lobby your implementers. If you think expression templates are the way ahead, tell them in no uncertain terms. I would remark though that expression templates absolutely annihilate compilation times. Templates do cost. They might save you on runtime execution. They might promote inlining. They might give you many ways of saying the same thing slightly differently without having to introduce errors caused by slightly misrepeating yourself. But the cost that you pay is in compilation time. And expression templates are no different. You would need to decide for yourself whether or not you want to use a simple naive implementation of matrix multiplication or whether you want to use expression templates. I hope that's answered everything. So let's consider how we can model geometric objects in C++. Now, the mathematician will tell you that a line is a set of points satisfying a particular qualification. For example, the x-axis is the set of points x, y, and r such that y equals 0. However, it's not a line of finite length. There are no endpoints. More useful would be a line segment with two endpoints. For example, let's consider this line segment. It starts at -3, 1 and ends at 5, 5. Now, this is the set of points x, y in R, such that -3 is less than or equal to x, which is less than or equal to 5, and y equals half x plus 5 over 2. So how might this be modeled in code? Well, two ways spring to mind: a struct with the gradient and the y-intercept for a non-finite length line segment, or a struct with the two endpoints. And I'm being a little coy here. I've been describing everything in terms of the set of points in R. Remember the dramatic music from earlier on, the foreshadowing. But of course, that's not actually a domain available to us on a digital computer. At best, we can only hope for the set of points in Q, and even then, we can't span that entirely with built-in types. There is not as yet a rational type in the standard, nor are any processors exposing that sort of thing natively, to my knowledge. Unless anyone knows any different, I'd love to hear from you. For example, we can't represent this number using the float type. And the reason why is one of precision. Floats are only precise to about 5 orders of decimal magnitude. And this will become a significant problem later on, and we'll return to this. But I need to take a little diversion now and talk about the Bernstein polynomial. So briefly, we start with the Bernstein basis polynomials, which look like this. The NV term is a binomial coefficient. I'm just going to let you take a look at that and take it in. It's simpler than it looks, I can assure you. In fact, let's look at an example. So B25 of x is 5 from 2 of x squared, 1 minus x cubed. So that's 10x squared times 1 minus x cubed. Now, a linear combination of these forms a Bernstein polynomial, which looks like this. Bernstein x equals the sum from v equals 0 to n, b to v, bvn of x, where the coefficients bv are known as Bernstein coefficients, or, and I'd like a drum roll here, please, to keep the musical thing going. Just get this drum roll running in your head. Bezier coefficients. So there we have it, more foreshadowing. But Bernstein polynomials are particularly useful for approximating continuous functions. And this is very convenient in the computing field, where we are dealing with approximation for discontinuous domains. Let's move back to lines and curves. We start with a straight line, which we observed satisfies the equation y equals mx plus c. But how do we represent this set of points? What are we actually trying to capture? I think we can agree that a vector of non-integer pairs would be a bad idea. For example, there are 4 billion floating point numbers, but apart from that, there is no guarantee that for each x value, the corresponding y value is available in the float domain, as shown earlier. Well, there's a gradient, and there's an intercept with the y-axis, so that should be enough for representing a line. A class called line with 2 floats or doubles, or whatever you're using for your number line, one called mGradient, one called mIntercept. But we very rarely deal with such abstract things. Usually we're dealing with line segments. So we need to constrain the class still further by adding the bounds to the line. So let's update the class to include P1 and P2. Let's call them Pbegin and Pend so that we can imply direction. So our constructor would include 2 points and work out the gradient and the intercept from those points. Now, having said that, you might be left wondering if the gradient and intercept are actually necessary. They're easy to calculate. Is catching each gradient and intercept worth it? And that depends on how you expect to use them. In my domain, we only care about the endpoint, and all the rest is lazily evaluated. Right, straight lines, that was easy. How about curves? Well, we have a problem here. There is one equation for a straight line, just one. There are many, many equations for curves. Again, in my domain, we are asking artists to create things by drawing with a stylus on a tablet. We can't ask them to model things using equations, although I do recall long ago, and I'm talking 25 years ago here, using 3D packages that had a palette of primitives to choose from. Regular polygons and polyhedra that you would simply insert into your scene and then deform and distort in some way. While it was effective, and it kind of did the job if you didn't want anything too realistic in appearance, it was utterly useless when it came to the normal development process of your typical artist. They want to work freehand. So are we back to capturing a vector of pairs of points? God help us, there must be a better way, and it turns out that there is. We can capture curves piecemeal and string them together. So let's take a look at a parabolic curve, which is the plot for y equals x squared. Now, you'll see all sorts of curves in this parabola. So, for example, between x equals -1 and x equals 1, you get a quarter of a circle. Whereas right up at the ends there, you're getting things which are very nearly straight lines. And that should be enough for us to be getting on with. But how do we store that? So we don't want to store a set of points. And in this case, we can't simply store coefficients of an equation. We need to store a start point and an end point, and some way of saying which part of the parabola we're tracing. So the best way to do that is to include another pair of points describing the x range of the parabola. So we can simply say, right, we want a curve. It looks like this part of the parabola, and we want to give it an orientation. And so you can imagine how this would work in a drawing program. You'd invite the artist to put down 2 points and then superimpose a parabola and invite them to move and scale the parabola until they got the desired curve. It's not enormously intuitive as user interfaces go, but it's a start, and it's what people work with in the 90s. So that's 4 points in total. Back to my domain. It would be nice if we can do better. Can we do it with just 3 points? Because it seems like moving the parabola around that pair of points with a mouse suggests we just need the 1 point, and it turns out that we can. So it's called a quadratic Bezier curve, and that individual point that I'm talking about is called a control point. Now, they're named after Pierre Bezier, who used them to design cars at Renault in the early 60s, which says a lot about the design of those cars then. Citroën, however, can lay claim to the study of the mathematical basis for these curves via Paul de Castellar. So curvy French cars in the 60s. It's all maths. So let's look at this maths. The general form of a Bezier curve is this. Bezier t equals the sum from I equals 0 to n of bin t pi for t between 0 and 1. N is the number of control points. P and bin is the Bernstein basis polynomial, which makes bt a Bernstein polynomial. So let's expand this for 2 control points, because it's just going to look much easier this way. So b of t equals p0 plus t of p1 minus p0. So this is the, if you were in Fergus's talk earlier, you'll have seen his request for a linear interpolation. This is linear interpolation in action. This is 1 minus t of p0 plus t of p1 for t between 0 and 1. And that's the parametric equation for a straight line. So I was lying a bit when I said there's just one equation for a straight line. Here's another one. But as t increases, you get a little more of p1 and a little less of p0. So we're back to our first class. Now, how about for 3 control points? Now, naively, it looks like this. It's a bit of a mouthful. bt equals 1 minus t of 1 minus tp0 plus tp1 plus t of 1 minus tp1 plus tp2 for t between 0 and 1. Just go with it. So this can be interpreted as the linear interpolant, 1 minus t to t, of corresponding points on the linear Bezier curves from p0 to p1 and from p1 to p2 respectively. Now, we can rearrange this equation like that. So now, b of t equals 1 minus t squared of p0 plus 2 1 minus t of t p1 plus t squared of p0. And this can be written in a way which highlights the symmetry with respect to p1. That. Now, the derivative for this with respect to t is that. Now, this is interesting because we can see from this that the tangents to the curve at p0 and p2 intersect at p1. And as t increases from 0 to 1, the curve departs from p0 in the direction of p1 and then bends to arrive at p2 from the direction of p1. So here's a couple of examples. I hope this diagram works. There we are. That's it. That's how they work. So armed with this equation and 3 control points, we can make a curve. So here's a curve class. And that covers our pen primitives. What about shapes? And do we have any further questions? Oh, don't see any. So life gets considerably easier now. We've defined our primitives, and everything else is just made up of those primitives, right? Well, kind of. Let's start with the simplest polygon possible. That's a triangle. So how would you define that? So let's see, we've got 3 corners, 3 edges enclosing a space. Seems to me that we just need to define a class with 3 points. What about a square? 4 points, easy. But this isn't going to scale. What about an arbitrary polygon or an enclosed space? Or how about a vector of points and a vector of edges joining the points together? How will that fly? We need to come up with a way of identifying the points. So we could try a vector of points and then a vector of pairs of integers identifying which points are connected in which order, or perhaps a vector of edges. Frankly, the cheapest thing to do is a vector of points and then infer the shape by iterating through them. If you want to cache the edges, you can do that, and that gives us our polygon class. And you can still have your triangle, square, and pentagon classes. They're a special kind of polygon, a regular polygon. Do we want to encode this fact? How about a base class? We could call it shape. Although, of course, we're not in the 1990s anymore, so please don't do that. One advantage of regularity, though, is that you can use that to infer other information. For example, a regular polygon can be completely defined by a center, a vertex, and the number of vertices and the orientation of the first point from the x-axis. Maybe you do want a regular polygon class and an irregular polygon class. I'm going to take a small diversion here and talk about 2D coordinate systems. The rule is that a coordinate system must uniquely define a point in the vector space which is spanned by the bases. The Cartesian coordinate system is established by taking the number line and rotating it 1/4 turn. Of course, it doesn't need to be 1/4 turn, but doing so makes the vectors orthogonal, which can be helpful. But you could have a coordinate system that looks like this. I've already described polar coordinates, where the Cartesian coordinate system works by traveling from the origin along the x-axis and then parallel to the y-axis. Polar coordinates travel along the x-axis and then turn about at origin by the second value. Can you think of any others? If you recall your complex analysis, you'll know that complex numbers can be described in a similar way to polar coordinates, which leads to interesting results about e to the power of I theta. And these are called log polar coordinates. And the trouble with these non-Cartesian coordinate systems is that they will never be as fast when it comes to rendering something. In my domain, I need to render to a rectangle, which means transforming and projecting everything along straight lines. But we still have to deal with curved shapes. So let's start with the circle. We can't describe this as a series of edges. We have to return to first principles and model it as a center and a radius. So we have a circle class. What about an ellipse? 2 foci and the major or minor radius are enough to cover this. 5 floats and a flag. But again, regular polygons are not enough. Regular curved objects are not enough either. Anyone heard of a stadium? Looks like this. And I have a direct use case for you. Has anyone played Asteroids? Right, I'm going to have to look away for a moment. Asteroids looks like this. Whoa, there we go. And when the ship gets destroyed, it has to respawn in the middle of the screen. But it has to do so when it's not in danger of being destroyed by any asteroids. And that would be terribly unfair. The simplest solution is to inspect every asteroid, see what area it's going to sweep out by its movement over the next 2 seconds, or fewer if you're feeling mischievous, and see if those areas intersect with the center of the screen. The area that the asteroid will sweep out is a stadium. Stadiums, lovely. So you can see that it consists of a rectangle and 2 semicircles. So we can store that as 2 foci and a radius. 5 floats again. But that's still kind of cheating, though. These first 3 examples were merely models of well-defined shape. What about an arbitrary curvy shape? Well, we saw in the example of the Bezier curve that we can use a single control point to create a segment of a parabola. What happens if we increase the number of control points? Well, certainly that can produce a huge variety of curves, and with an overlapping beginning and end point, that should give us a closed shape with a curved outline. However, as the number of control points increases, the calculations become considerably larger to undertake. Remember, the polynomial has per point terms, so the more points, the more work is required for each iteration through the parameter. The proper solution is to simply have a succession of Bezier curves. One approach would be to have a set of pairs for the start point and control point and an optional endpoint for an open curve. You can make a circle or ellipse from 4 Bezier curves. You can make a stadium from 4 Bezier curves and 2 straight lines. But that would need an additional flag for each segment to say whether or not it was a curve. But there is in fact another way to implement a shape, and that's with a bicubic Bezier patch. This beast is modeled like this. Beautiful creature. P is the patch evaluated over the unit square, where u and v range from 0 to 1. B is the Bernstein polynomial, and this deforms the unit square in the dimensionality of the control points, k, which is an I by j array of points. 16 will suffice, making m and n equal to 3. I'm not going to write this out. It's a 16-term polynomial, where each term is the product of 2 Bernstein polynomials, but it suffices to say that it's an expensive way of describing an irregular polycurve in 2 dimensions. But in 3 dimensions, it's marvelous. I'm going to check for questions. I'm seeing none. So I just want to take a quick diversion into the most knotty topic in computational analytic geometry, and that's intersection. 2 lines intersect if they cross over. 2 polygons intersect if they overlap. But we need to be a little more rigorous than that. Recall that a line is a set of points, so 2 lines intersect if there is a point that is common to both sets. Let's revisit 2 lines. Y equals x minus 1, y equals 2x minus 4. Do they intersect? Well, they aren't parallel. They have different gradients, so they must do. Subtract one from the other, and you get this. They intersect where x equals 3. So far, so good. Let's try another. Y equals x squared, and y equals x plus 3.9. Do a bit of maths, solve a quadratic equation, and you'll see they intersect in 2 places, 0.5 plus or minus the square root of 16.6 over 2. Now that square root is a problem. That number can't be represented on a computer. It's not a rational number, and only rational numbers can be correctly represented. And even then, not all of them, as we stated earlier. But it's worse than that. Consider these 2 straight lines. Y equals x over 3, and y equals x minus 2.3. They intersect at x equals 3.45. That number can't be represented in binary floating point arithmetic at all. Here's another thing to worry about. How many orders of magnitude is a float accurate to? So here is a picture of the distribution of float in 2 dimensions. And as you can see, the concentration of numbers increases towards the origin. And we should expect this because there are as many rational numbers between 0 and 1 as there are greater than 1. And there is a fundamental problem with total war, and this is the game that I make. We model field warfare on a large scale. Battlefields are about 10,000 meters square, and combat takes place at a much finer resolution. If this were an in-person conference, I would request a volunteer. The brave volunteer would come up to the stage to tumultuous applause. And when they reach the stage, I would say, now I'm going to try and punch you in the face. I'll miss, I promise. And I would, of course, miss. I'm not a monster. I would miss their face by about 2 centimeters. Now, how many centimeters are there in 10,000 meters? There are, in fact, 1 million. And if we try and model that using 5 orders of magnitude, we'd get that wrong. And I would, in fact, probably hit my volunteer. Now, we would need to use a type with greater precision, but that would mean either doubling our memory budget for the coordinate system by moving to double, or losing our hardware advantage by moving to a custom type in software. Of course, we could move to integer maths and work entirely in millimeters. 4 billion millimeters will actually get you from London to Ankara, capital of Turkey, which is rather larger than our usual battlefields. And it would send our artists and tooling folk absolutely mad if we were to drop SI units. But of course, fists and faces are quite big things. In general, the number of occasions in which there is going to be a false result is pretty small. But consider an animation where a sword swings against another sword. If the paths intersect, we get a hit. But swords are thin things, though, so there is very little tolerance indeed. Also, swords do move pretty fast, so there is a danger that in the process of sampling, the sword passes through the other sword entirely. Worse still, moving 2.3 meters to the side may make a difference. We really are in a lot of trouble when it comes to intersection. How do we deal with a prospective function like this? Well, the thing is, we can't. So what we have to do is add an additional parameter to describe a tolerance. So let's see if you remember the difference between float min and float epsilon. Float min is the smallest number that can be represented with float, while float epsilon is the difference between 1.0 and the next float representable number. Epsilon is used in maths to signify an arbitrarily small quantity. If we want to see if 2 points are the same, we will need to specify how samey they need to be. Since some noise has already been introduced by sampling the plane, we need to account for that in our function. So our function would need to look something like this. To allow an error tolerance due to sampling, one of the things I always look out for during code reviews for new starts is the presence of direct comparison of two floats. It is almost never what they meant. Dissuading people from using the equality operator on floats is a tough job. And I will pause for questions and a sip of water. So let's review our set of types in the absence of any questions. So first, we need a coordinate system and means by which to perform transformations. I'm hoping to secure a subnamespace called math so that we can reuse the name vector. So we could start with stud math vector. Interestingly, math is in fact English, not American. Math and maths are both printers' abbreviations. Math was first used by the English, and maths was first used by the Americans. Over the course of the past couple of hundred years, it's swapped over. So I'm not enormously unhappy about the continued use of the word math. Anyway, I want to see specializations so that I don't need to be messing around with angle brackets. So for example, I would like to see something like this. A float 2 is stud math vector over some kind of fixed size vector engine that takes two elements that are floats, and float 2, which is a matrix over some kind of fixed size matrix engine over float 2 and 2. I'm sure that's entirely self-explanatory. I should point out that since writing this presentation, indeed in the past week or so, we've made some quite dramatic changes to the linear algebra proposal. We've got rid of many of the engines. If you've been keeping up with what we've been doing, we've got rid of many of the engines and replaced it with one, and made use of concepts and requires clauses to make things much easier. Honestly, I do recommend you take a look at concepts and requires clauses. Your APIs suddenly become a lot smoother, a lot nicer to use, and a lot harder to use incorrectly. Anyway, better still, I would actually like this to be implementation defined so that implementers could use their knowledge of the target to implement the vector, for example, using SIMD registers and intrinsics to do the job. This is really important. It strikes at the heart of one of the problems in my domain. Game dev people bypass the standard as far as possible. They are never sufficiently performant. We know more about our domain than the library implementers, and we end up implementing a lot of the work ourselves. For example, we will bypass exception handling and RTTI. The current linear algebra proposal is very flexible and will accommodate many, many use cases, but one of the largest use cases for linear algebra in practical computing is in geometry. My linear algebra engine, the one that I've written for myself, is super tuned for geometry. The matrices and vectors are formed of SIMD registers. the functionality is supplied via SIMD intrinsics because I know all about my target platform. It only has to compile for x64 machines with recent Intel processor instruction sets. Anyway, next on to path. A path segment may have 3 or 4 control points. If it has 2 control points, it's a straight line. If it has 3 control points, it's a quadratic Bezier curve. Is there scope for a cubic Bezier curve, a path with 4 control points? There may be. Such curves are used in motorway design, for example, to smoothly navigate past points in the road. I haven't gone into much detail about them because we then get into spline territory and have to start comparing B-splines with Bezier splines, and that's out of scope for this talk, and probably for this proposal, in fact. So a path is therefore a container of segments, which may have a varying number of control points, which sounds like a use case of assisted variant. Now, perhaps you want 3 kinds of path, one composed of just line segments, one composed of Bezier curves, and one composed of mixed lines and curves, polyline and polycurve. And then we want special closed paths, or polygons. We might want a regular polygon class that looks like this, which we can simply describe with a using statement. There we are. Triangle is a regular polygon of 3 points in the coordinate system supplied in the template. Then we have circle, ellipse classes. Stadium seems like it might be a little too specialist, to be honest. But finally, we have a patch class consisting of 16 control points. And I say finally because, as I remarked, 3D seems like a bit of a reach for the time being. If someone else wants to add it on, then they can do so. I don't believe any of this precludes arbitrary dimension objects. I've still only described vocabulary types. There's no functionality yet. And this is important. I'm not a great fan of giant APIs. We already have one example of that, which we can't go back from, and that's the basic string. An enormous number of member functions. I think all the functionality of geometry should be implemented as free functions. But which ones? What do we want to actually do? Well, we've already described intersect, and it should be able to offer an intersection of any 2 objects, not just lines. More fundamental than that is distance, which gives you the separation of 2 points, and length, which gives you the length of the path. And then we're into 2 dimensions. Contains will tell you if one shape is completely inside another. Area is analogous to length. Perimeter is equivalent to length. Centroid gives you the central point of a polygon or a patch. While envelope gives you the axis-aligned rectangle that bounds a shape. There isn't actually that much to do for geometry, so this might be a quite snappy little proposal. Stay tuned. Thanks for listening. And ask me some questions. I, of course, have 30 seconds to wait. All right, so my first question is, how far down the line is the linear algebra proposal from a standards committee point of view? Well, proposals have quite a long path. Now, they start off in a study group. This one started off in study group 14, which was for game dev and low latency. Then it went into study group 6, which is the numeric study group. Then it went into LUGI, which is the Library Evolution Working Group Incubator. Now, this is where papers are kind of, it's like overflow for the Library Evolution Working Group, and it allows us to firm up a paper. Since the advent of the plague, the events of this year, the committee's been meeting online quite extensively, and Linear Algebra has been able to take quite an interesting, we've had a lot of good feedback, and it's been able to be reviewed quite extensively. There's already another linear algebra proposal in place which wants to put the BLAS interface into something nice and C++y. We're expecting revision 7 to come out this time next month, at which point we think we'll be pretty much finished and we'll be ready to start wording. Once we've started wording, the paper will go to the library working group, and once the library working group have taken a look at it, we simply have to wait on their pipeline being emptied. Now, this means that we're pretty much done. If you want to take a look at it, it's P1385. Yeah, talk to me about it afterwards. But we're good to go. Since you say that game developers like to reinvent the wheel, don't you think that game developers would always create their own math library, no matter how optimized the STD version would be? Well, that depends, doesn't it? Some game developers want to spend all their time making the code faster and faster and faster and finer and more careful, rather than just writing the game. I'd like to think that I'm going to be enabling people who just want to dive in and get straight to work, rather than having to write their own linear algebra library. There's a big problem at the moment with game dev, which is that lots of people come in and they'll write all the engines, but they're not actually writing the games. Game dev is about a lot more than simply writing maths libraries and geometry libraries and graphics libraries. You know, there's plenty of people who will do that. But actually what I want to do is make sure that the standard can allow you to throw something together really quickly. You know, you'll have all the stuff in place to simply do the maths for 2D. So what standard version are you targeting? Well, I think we can get this in for C++23. It should be in the next standard. As I say, it depends very much on the library working group queue. They have a lot of papers to provide wording for. Let me just see, what's the next one? How about reusing stud chrono ratio for increased precision? Yep, that could be done. Yeah, you could have a vector, or you could have a matrix of stud chrono ratio types. That would be interesting. That would work. More interesting, I think there's an elastic integer, elastic fixed point. Oh, what's it called? There are papers in process for adding further numeric type representations into the library. There isn't a ratio, there isn't an explicit ratio type, but maybe chrono ratio would do the trick. How would the linear algebra proposal play with one that's BLAS-like? Could we have at most one of the two? Well, that's a really good question. Thank you, Fergus. As I say, the BLAS proposal is already in flight and is further advanced than the my linear algebra proposal. Now, my linear algebra proposal sets aside objects like matrix and vector and the operations between the two, so that you can do matrix multiplication between types of mixed precisions and things like that. The implementation that I'm expecting to provide, as I said, is simply either a naive call out to some const extra functions or expression templates. But you could indeed use the BLAS to provide all those kernels. And now that the BLAS is rapidly making its way towards the standard, it would be quite trivial to implement the entire linear algebra library in terms of BLAS operations. And this would be a great idea because BLAS is optimized, really, really magnificently optimized for many, many different hardware platforms. In the question, you do say, could we have at most one of the two? We could have just one of the two, but I think that would be a very disappointing opportunity missed. Right, next question. How should intersect handle special cases, such as one line just touching the other, but not really intersecting? Depends what that means, really, doesn't it? By having a tolerance, you can say, well, is it within this, this tolerance of satisfying intersection? So you'd have to pass in that third epsilon parameter. How about conversions between polygonal types? Ooh, I don't think I understand that question. If you want to ask a fresh question about that, I'll have a go at answering. Is spheres and ellipsoid support completely out of the question for your geometry proposal? Yes, I want to stick with 2D. I think you should bring the smallest proposals you possibly can to the standard library. If you want to put in 2D and 3D and everything else, it will become impossible, absolutely impossible to get the proposal in. It would take forever. Do you anticipate any use of mixed precision in the implementations of the proposed free functions? Yep. I think that, well, by which I presume you mean float and double. That's probably going to happen. So you would require overloads to support all those. Can you clarify the context of the image regarding the battlefield? it is subdivided into something like an acceleration structure. Is this relevant to precision or purely coincidental? It is relevant to precision. If the battlefield is 10 kilometers wide, then that means that the precision of impact is going to be much worse at the edges than it is at the center. Because there are far more floating points, because there are far more elements in the set of floating point representable numbers in the center of the battlefield than there are at the edge. So I guess it's coincidental, but I'm going to have to think about whether or not it actually is, if they're two different sides of the same sort of coin. Right, how about conversions between polygonal types? Yes, right. I'm just going to skip Markov's question and say, Max Langhoff, isn't using floating point numbers in the context of games, i.e. reproducibility of result across machines for multiplayer replay, pretty dangerous? Yes. Yes, it is. It's enormously dangerous. We have to go to considerable lengths to make sure that our code does indeed reproduce correctly across machines. Things like order of execution will destroy you straight away, because floating point A plus B is not necessarily the same as B plus A when A and B are floating points. It's not commutative. I'm happy to talk at length to you about this later on. How do you currently handle floats at your company? With great care. We use floating point arithmetic because we have a considerable hardware advantage in so doing, and so we just have to work with the risks that it presents. Right, a bit off topic, but apart from code reviews, any other suggestion to avoid double comparison creeping into the code base? No, code reviews. Or just outlaw the use of the word double so you can grep your code base for it. If you see double, you know that something's gone wrong. Right, so you have some regular polygon, but you want to convert it to a more generic representation. Do you know what? I think you're going to have to talk to me after this. I'm really not convinced that I know what you want to do. Would this work with fixed precision numeric types such as CNL? Should do. All you need to do is ensure that you have the operations available to you for addition, subtraction, multiplication, and division. That's all that's required for geometry. Right, I shall be lurking at my table in Const West. And thank you for turning up. I hope you've read the credits and acknowledgements screen. The C++ standard graphics proposal is still underway. Goodness knows when it'll see the light of day. And of course, as you can probably imagine, this geometry proposal is simply a part of this, as is the linear algebra proposal and my upcoming color proposal. Thanks for attending. I hope you enjoy the rest of the conference.